Okay, so now we're done talking about one-dimensional kinematics, and we're going to start talking about two-dimensional kinematics. I introduced vectors last time. So 2D kinematics of particles. And when we talked about 1D kinematics of particles, I started by defining position, how you come up with a number for position. I'm going to do the same thing now in 2D. Now, a lot of these things that were numbers in 1D are going to be vectors. So remember, so before we can come up with equations to deal with kinematics, we need to define the position vector. And that is P with a vector symbol over it. The velocity vector, that's V with a vector symbol. And the acceleration vector. These are all vectors. So velocity vector, V, and the acceleration vector. A with a vector symbol. And so I'm going to start with position, and with each of these three, position, velocity, and acceleration, I'm going to give you like a definition of it that you should try to keep in your head. And I'll say some other things about it that you should try to remember as you work through problems. So the first one is the position vector. Well, when I started talking about position in 1D, I gave you two things that you had to choose before you could put a value to a position. Those were the zero position and the positive direction. In 2D, there's sort of a similar thing, but it changes a little bit. So in 1D, we needed to choose the zero position and the positive direction before we could put a position to a location. In 2D, it's similar. But now we're talking about stuff in the plane. So in 2D, you have to choose the location of the origin of the coordinate system So the location of the origin in, the real world. So again, you can think about, imagine putting down a piece of tape or something to indicate where the origin of the coordinate system is. And second, you have to choose an orientation of the coordinate axes in the real world. Orientation of coordinate system axes. In the real world. Once you've chosen those, the position vector P is the vector from the origin, from the coordinate system origin to the object. Okay, so for example, if your coordinate system is like this, and the object that you're tracking is here at some instant, then the position vector goes from the origin to the object. And one thing that you should remember, because this makes it easier to visualize the position vector, is the components of the position vector are just the coordinates of the object. Okay, so for example, if you have a coordinate system like this, and your object that you're tracking at a single instant is here, then what are the coordinates of that object? So we're at x equals 4, y equals -3. So the coordinates are 4, -3. And so that means that the components of the position vector are 4, -3. The units for position, we're going to see that the units are exactly the same for everything in 2D as they were in 1D. So units of length and units of position in 1D were length units. And the SI units then were meters. And it's exactly the same in 2D. Okay. Any questions about the meaning of the position? So like, if you want to visualize the position vector, just think of yourself as plotting, the coordinates of the object in the coordinate system that's chosen. Okay, so now what about the velocity vector? I have a little more to say about the velocity and the acceleration. Velocity measures how quickly the position vector is changing. And so a velocity of 0 means that the position is staying the same. The thing isn't moving anywhere. So remember that all vectors have two properties. Anyone remember what those are? Magnitude and direction, okay? And nothing else. So vectors don't have locations. They don't have anything like that. They just have a magnitude and a direction. So what are the magnitude and direction of the velocity vector? Okay, so all vectors have two properties. Magnitude and direction. For velocity, the magnitude of the velocity, that is like, you can think of that as the length of the arrow, is the speed. And the direction is the object's instantaneous direction of motion. You know, the direction that the object is moving at exactly that instant. The units for velocity, just like they were in 1D, are units of length divided by time. And that means that the SI units for velocity are meters per second. And there are three really important facts that you're going to want to keep in mind as you do problems involving velocity. So three important facts about the velocity vector. The first one is often you're going to need to calculate the components. So you're often going to need to calculate the components of V from a speed and a direction. Okay, so an example of this is a problem will say something like, at the start of the motion, the object is traveling 10 meters per second. At an angle 30 degrees above the horizontal. Okay, well, that means that if you choose a coordinate system where the x-axis is horizontal and the y-axis is up. Okay. The velocity vector looks like this, where this angle is 30 degrees and the magnitude is 10. Okay, and you've done vector problems like this, or you will, you know, if you still have to do the vector stuff today, this is the kind of stuff you'll do. So how would you come up with the components of that? The velocity vector components then would be 10 times the cosine of 30, 10 times the sine of 30, and that comes out to be 8.66 for the x component and 5 for the y component. Another way to say this would be to say that the x component of the velocity is 8.66 and the y component of the velocity is 5. Okay, so pretty close to every problem, rather than giving you velocity components, it's going to give you the direction the thing is moving, and it's going to give you the speed, and you just have to combine those to come up with the velocity components. Okay, the second important fact about velocity is if an object is dropped, you know, if it's dropped rather than launched or thrown or whatever, then at the instant of release, the instant it's released, the object's velocity is the velocity of whatever it's dropped from. Okay, so for example, if a problem says that a ball is dropped from a car that's moving horizontally, at 20 meters per second, then in order to figure out what the velocity of the object is at the instant it's released, we just have to figure out the velocity of the car at the instant it's released. So again, I'm going to show a coordinate system like this, where the x-axis is horizontal, and it says the car is moving horizontally at 20 meters per second. So what are the components of that velocity vector of the car? Think of the coordinates of the head of that vector. 20, 0, yep. So at the instant it's released, the object has a velocity vector that's also equal to 20, 0. Or again, if you separate those components, the x component is 20 meters per second, and the y component is 0. Okay, so if an object is dropped, so this is what happens if an object is dropped from a car. What if an object is dropped from a building? Well, the building has a velocity of 0, and so the instant you drop something, it has a velocity of 0. Or if you drop it from the ground has a velocity of 0, so the thing has a velocity of 0 when you drop it. Okay? Any questions yet? And then the last one, this is one that probably, a lot of this stuff, maybe if you had to guess at how these things worked, you'd be right about some of your guesses. This one is one where you probably wouldn't be right, so pay attention to this one especially. So remember in 1D, when an object reaches its highest point in projectile motion, the velocity is 0. So you might think in 2D, when an object reaches its highest point, like a projectile, you know. So in 2D, when a projectile reaches its highest point, you might think that the velocity vector is equal to 0 at that instant, but that's not quite right. What it really is just the vertical part of the velocity is equal to 0, which we're always going to have as Vy. So Vy is equal to 0. But the key thing to remember is not the x component of the velocity. It is not 0. Okay? And I think this example, it'll make sense if you think of this example. This is like a baseball guy. Okay, so he threw this ball. Okay, say he threw this ball 100 miles an hour. You know, he throws this ball really fast. And imagine if you knew exactly where he was going to throw this ball, and you set up a ladder and stood on top of this ladder so that exactly at the instant that this ball reached its highest point, that ball reached your head. Okay? Are you picturing what I'm talking about here? Well, if it was true that when the ball reached its highest point, its velocity was 0, what that would mean is that this ball, just as it got to your head, the back of your head, it would just kind of gently nuzzle up against it, be not moving at all when it hit your head, and this whole thing would be just a joyful undertaking, you know what I mean? But you know from experience that that's not a good assumption to make, and that this would hurt quite a bit, you know? The reason that is when this ball is thrown, it's moving a total of 100 miles an hour. So that might be an x component of 95 miles an hour and a y component of 15 miles an hour, you know? The magnitude of that vector has to be 100. Well, the y component of that velocity when it reaches the highest point is going to be 0. Okay, so the thing that's initially 15 miles per hour, that is 0. So it has slowed down a little bit, but nothing has slowed down the x component of the velocity. And so this thing is still going to hit the back of your head at 95 miles an hour. And that's going to be very unpleasant, you know? So remember this picture when you think about something in 2 dimensions reaching at the highest point in its flight. It's not Vx equal to 0, it's only Vy equal to 0. Okay? Are you with me on that? Anybody have any questions about that to ask, to clarify anything? Okay, so that's pretty much everything you need to know about velocity. And so now the acceleration vector. So remember I said velocity is a measure of how quickly the position vector is changing. Acceleration is a measure of how quickly the velocity vector is changing. So acceleration is a measure of how quickly the velocity vector is changing. Well, what that means is if the acceleration is 0, the velocity isn't changing at all. Okay? So you can think of these as exactly equivalent statements. Constant velocity means exactly the same thing as 0 acceleration, 0a. Okay. In 1D, if you have an acceleration, if acceleration isn't 0, it means that the speed of an object is changing. Okay, that's the only thing acceleration can do. So I'll say non-zero acceleration means speed change. In 2D, it gets more complicated. Non-zero acceleration, a non-zero acceleration vector can mean two things. First, it can mean that the speed is changing. But in 2D, you can actually have acceleration even if the speed is staying constant. So it can mean the speed is changing, but it also can mean that the object is turning. Okay, so why is that in 2D and why isn't it in 1D? Well, it's pretty simple why acceleration doesn't cause turning in 1D. There's no such thing as turning. We're just talking about motions along a straight line. So all it can do is just go forward and back. There's no such thing as turning. Okay. Remember that acceleration just means the velocity is changing in some way. And remember that velocity has a magnitude and a direction. Okay? The magnitude is the speed, and the direction is, the direction the thing is moving. So the speed is changing if the magnitude of the velocity is changing. But the velocity is also changing if just its direction is changing. And that's when this object is turning. Okay, so we're going to talk about this quite a bit, like interpreting this, trying to figure out what's happening, what the acceleration is when an object's turning this way or that way, what the acceleration is when an object's speeding up or slowing down. But for now, this is all I'm going to say about this. There's a new thing that's introduced into these motions. That's the direction changing over time, and that is also an acceleration. Okay? Actually, let's think about an example of this. If you're in a parking lot, a big empty parking lot in a car, and you're going 20 miles an hour, it's empty, so that's all right to go 20 miles an hour. And you go 20 miles an hour in a car and you turn in a circular path, you can feel that acceleration. That feeling in your stomach, that's the acceleration. And that acceleration that you feel, you're staying at 20 miles per hour. So it's not coming from the speed changing. It's just coming from the fact that you're turning. Okay. And most the accelerations you feel on amusement park rides are mostly the accelerations of the direction changing of the thing turning more than they are the acceleration of speed changing. Okay. The units for acceleration. Again, it's the same as in 1D. It's units of length. Divided by time squared. And so the SI units for acceleration are meters per second squared. And I've mentioned this once before, but if you can remember what the units are for the different quantities for position, velocity, and acceleration, it can make it a lot easier to make sense out of what information is being given to you in a problem, because you can just look at the units, Okay, there's one thing I want you to notice about acceleration. In free fall and projectile motion problems, I am always going to do this, and I think you probably should too. Just always choose your y-axis pointing up. So in free fall and projectile motion, I'm getting ahead of myself. The acceleration vector is always 9.81 meters per second squared down. Okay? And if you choose your y-axis to be up, then the components of this are 0 for the x component and negative 9.81 for the y component. The magnitude of that, 9.81 meters per second squared, is called lowercase g. So another way that you could write this is the acceleration for something in free fall or projectile motion is 0 for x and negative g for y. Okay. Any questions about acceleration? Okay, so now what we're going to do is I'm going to introduce the constant acceleration equations in 2D. And we're going to solve problems in 2D very similarly to how we did it in 1D. So now we're getting into the constant acceleration equations. in 2 dimensions. Okay, well, first we have to define a couple things just like we did when I introduced it in 1D. So PI and VI vectors are the position and velocity vectors at time equals 0. And PF and VF are the position and velocity vectors at time final, just like they were in 1D. And a subscript x always means the x component of a vector. And a subscript y always means the y component of a vector. And with these definitions, we have 6 constant acceleration equations. These are x and y versions of our 1D constant acceleration equations. So here's what they are. So we know this one from before. And we have x and y versions of this equation. So if you think of starting with that original V final equation from 1D, now one of these has all x components on the vectors. Notice there's no components on time. Time final still means the same thing it did before. And then we also have one for the y components. Okay. Then next we have the PF equations. So PF is equal to PI plus VITF plus 1/2 A TF squared. And we have 2 of those. The first one has all x components. And the second one has all y components. And then the last one is 2a times the quantity PF minus PI is equal to VF squared minus VI squared. And we have 2 of those. The first one is all x components. And the second one is all y components. Well, with 1D, remember we looked through all of these equations, and we had 6 variables that showed up. Well, now with the multiple components, we have almost twice that many. Not quite twice that many because T doesn't have components. TF doesn't have components. But so here are all the variables, and there's 11 total variables. TF, AX, AY, PIX, PIY, PFX, PFY, VIX, VIY, and VFX, VFY. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So I'm going to give you a general set of steps for using these in 2 dimensions, and then we'll just get into example problems, and we'll just do a lot of example problems. Like our next class, we'll spend like pretty much the whole time just doing example problems. But first here, the general steps to follow for 2D constant acceleration equations. So the first step is, in the real world, choose an origin location and a coordinate system axis orientation. And then choose an instant corresponding to time equals 0. And an instant corresponding to time final. Okay, so these are the same, really the same 4 choices you made in 1 dimension. Except instead of a 0 position, you have a coordinate system origin. Instead of a positive direction, you have a axis orientation. Second, well, what was the second step in 1D? What? The second one that I always said is list out what you know and what you want. So that's what we're going to do here. So we're going to list the variables we know and what we're trying to find. Third is where you try to find the equation. And you know you have an equation that's going to work when, so you want to find an equation that has the wanted variable and every other variable in the equation is known. Was that the end in 1D? Do you remember? There was one more that you hope you didn't have to use, but sometimes you don't. And that's the one, what if there's no equation that works? And it's basically the same in 2D as it was in 1D. If no equation works, solve for TF is the one that you're going to want to solve for in the problems we do. So solve for time final, and then go back to step 2. And I want to show you why time final is such a useful variable to know in 2D. If you look at these 6 equations, notice that x variables never show up in the y equations and vice versa. Okay? The only variable that appears in both x equations and y equations is time final. Okay? So if you can figure out an equation that lets you solve for time final, then knowing time final, you can use that in, the other type of equation. So a lot of times, like, we'll use these two together pretty often. What'll happen more often is we'll use the y equation to find time final, like to find how long it takes to hit the ground or whatever. And then we'll take that time final that we solved and plug it into the x equation to figure out how far it went horizontally before it hits the ground or something. Okay? Okay, let's do a quick example problem. So let's say that a ball is thrown horizontally from a height of, let me give a speed. So let's say it's thrown horizontally at 10 meters per second. From a height of 4 meters. How far does the ball travel horizontally before it hits the ground? Okay, so it's going to look something like this. Here's the ground. This distance is 4 meters. And the ball is going to start out with a horizontal velocity. And it's going to travel in a parabolic path like this. And this is the distance we want to calculate. Okay? Well, the first step is to choose an origin location and a coordinate system orientation, and then an instant for time equals 0 and time final. I'm going to always, when I do these problems, put my origin at the lowest point in the problem, right underneath where the object is at the start of the motion. So, and I'm always going to put my y-axis pointing up. So this is pretty much the way I'll always choose my coordinate system. And then what about those times? What do you think we want to choose as our time equals 0 instant? Yep, the instant that it's launched. Because we know some stuff there. We know its height and we know its speed and its direction. So we can figure out its velocity. And what do you want to choose as our time final instant? Yeah, right. The instant it reaches the ground level. And now that we've done all those, we can think through the variables and think about what we know and what we want. So here's a list. And let's just think through them one by one. Okay, do we know time final? Do we know what the stopwatch says when it hits the ground? No. Do we know anything about acceleration? It's free fall, so we know everything about acceleration. My y-axis is up. So my acceleration vector is 0, negative 9.81. So we know the x and y components. Do we know the position at time equals 0? Remember, that's the coordinates of the object at time equals 0. So you can see that that's 0x, positive 4y. You with me on that? I'm not even paying attention anymore. This is stupid. So this is 0 for x, 4 for y. Do we know anything about the position at time final? We don't know the horizontal component of the position, like we don't know the x coordinate, but we do know the y coordinate is 0. So Pfy is 0. And Pfx is what we're trying to find. What about the initial velocity vector? Do we know that? Well, it has a magnitude of 10 meters per second, and it's acting exactly in the x direction. So what would that be as a vector? Like you can think of it as, okay, it's going to be equal to 4 for x, 0 for y, and that comes from thinking about it this way. If this is the coordinate system, and this is the velocity vector, it has a magnitude of 10, then what are the coordinates of the head? Oh, this shouldn't be 4, it should be 10. Okay, so it's just the coordinates of that are going to be 10 for x and 0 for y. So that's where that comes from. And then do we know anything about the final velocity? No, so that doesn't go anywhere. Okay, is there any equation that works for these? If you look through, you'll see that there is not. So no equation works. So the next question is there an equation that works for us to find time final? And the equation that works for time final is PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. So this says 0 is equal to 4 plus 0 times time final is 0 plus 1/2 times negative 9.81 times TF squared. So this is minus 4.905 TF squared. Now add 4.905 TF squared to both sides. Divide both sides by 4.905. Can someone do that for me? I don't have my calculator out. So TF squared is equal to about 0.8. 0.8 something.
Well, if you round 0.82, about 0.15.
Okay, I'll just use 0.82. And then take the square root of that. So TF is plus or minus. What's the square root of 0.82? About 0.9 exactly, right? Yeah. 0. I'll call it that. And then this is in seconds. Do we want the positive or negative? Positive. We still don't have negative times. And so now that we've found TF, that's one more thing we know. And we can look for an equation to find PFX. So the one that works is this one. So PFX is what we're trying to find. PIX is 0. VIX is 10. So 10 times 0.9. This is an easy pitfall an easy trap to fall into. You're so used to saying the acceleration in free fall is 9.81 or negative 9.81. But remember, this is the x component. And in free fall, the way we do the coordinate system, the x component is 0. And so this is all just equal to 0. And so you get PFX is equal to 9.0 meters. Any questions about that? A lot of the stuff that you know from one-dimensional stuff you can still use in 2D. So you just, really, I would recommend try focusing on just the things that are different, and you'll be able to do this stuff without a ton of extra memory taken up in your brain, you know what I mean? Okay, that's all.